Hi, my name is Dylan. I'm a backend engineer on the database sharding team at GitLab. As the team is currently exploring the idea of sharding our database by top-level namespace, we expect we will inevitably need some approach to moving data between shards for initial balancing and future automatic rebalancing of shards. I'm going to demonstrate a proof of concept implementation for moving top-level groups between shards using some lower-level features of Postgres that should guarantee the move is both correct without gaps or race conditions in the data, efficient for larger groups, and with minimal write-down time to minimize user impact. In my terminal window, I have two Postgres connections using PSQL. One is to the main GitLab HQ development database for my GDK, and the other one is to an empty replication database. So let's first start by checking the main database for my GDK, which has 7,300 issues in it. In the destination database, we will just truncate all these tables to be sure they are empty. I'm only going to demonstrate moving namespaces and projects and issues in this demo to simplify things. So we now have a database with nothing in it, but it has the exact same schema as the main GitLab GDK database. In order to copy a group across, I've created a sidekick worker that I'm just going to execute directly from the command line here. It is going to attempt to move the top level group with ID 22, which happens to be the GitLab org group in my GDK, copy that data from the main development database to this other GitLab HQ replication test database, which we can think of as the destination shard where we're moving it to. So if I run this now, it will perform an initial copy of the data, and it should also stream any updates that happen while it's running. If I check now for the count issues, I can see that there are 72 issues that are being copied across. These 72 issues all belong to the top level or GitLab org group on my GDK, as opposed to the 7,300 issues which exist throughout the entire instance. So we've successfully copied the projects, issues, and namespaces related to that. Since this has no subgroups, it's just one namespace, but there are two projects within that namespace that have been copied across. Now I'm going to demonstrate what happens when I create a new issue while this worker is running. It should copy that issue across. So here I have in my browser a new issue tab. So I'm going to create a new issue with some title and a description. After I create this, it should be picked up by that worker and copied into the new destination database. New issue there, and if I check the count of issues, I now have 73 as opposed to 72 issues. The worker has outputted the SQL, which corresponds to the statements it needed to run in order to synchronize the data, which when you create an issue in GitLab, it does an insert into issues, and then it also updates something about the issue after the fact. And those are the two queries that correspond to the data that was synchronized between the two places. Now, I'm going to discuss the setup that was necessary to get this working. So I have a sidekick worker, and that's the file I have open right now. In this file, it describes a bunch of setup steps that I followed in order to get all of this working. The first one is that I needed a plugin for Postgres in order to output the raw SQL necessary in order to synchronize the data between the source database and the destination database. This is a plugin that implements a custom logical decoder, which I'll get into in a second, in order to track the updates from the first database and format them as raw SQL that I can apply to the second database. The steps for doing that are cloning this repo and then editing something and running make install. Next, I needed to make some configuration changes to Postgres to get this to work. I needed to set wall level to logical, and I needed to increase the number of application slots which will be used for synchronizing the data later and restarting Postgres there. The next part is a little bit more interesting. I needed to create a destination database with the same schema as the first one, but without any data in it, and using pgdump, createdb, and pgrestore, I was able to do that. Then Once I started copying data across in my testing, I found that I was very quickly violating a bunch of foreign key constraints. Some of these foreign key constraints are just because I am not copying all the data across for now. Some of these foreign key constraints are going to be constraints that will not work when we have a sharded database. The most obvious one is going to be user, and that seems to be a foreign key that's referenced from a lot of tables in GitLab, since the user won't be sharded across the shards like the other namespaces will be. And some other ones represent features that may or may not be problematic with the sharded database, but I'll get into that in a second. So, for example, to show you how the code works now, the code works by creating a so-called replication slot in Postgres. And this logical replication slot uses a plugin, and that plugin interprets everything that goes into the write-ahead log for Postgres, transforms that to raw SQL, and allows a consumer to consume that raw SQL from somewhere else, in this case in our Ruby code, and then write those statements to another database. That can be thought of like a queue of updates that happened while the move was ongoing. But after creating this, we need to also get an initial copy of all of the group data that existed just before we created this queue, so that we can have an exact copy. Luckily, Postgres has this feature of snapshot IDs or snapshot names, which corresponds to a specific snapshot of what the database looked like at the exact point in time when you created the replication slot. So the first thing we do is we create the replication slot. The next thing we do is get that snapshot ID, and we use Postgres's repeatable read transaction levels and the exact snapshot ID to copy exactly what the database looked like at that point in time to a CSV file, and then load that CSV file onto our destination database here, reading the CSV file and writing it into that. And I do that for each table that we're copying across, which happens to be the namespaces, projects, and issues table only. Once that initial copy is done, we now expect in a live system that there could have been updates happening while the initial copy was running. So therefore, we need to consume this replication slot to consume all of the updates that happened. So right now I have a fairly naive implementation, which is just a loop that is reading from that logical replication slot, finding insert or update statements that correspond to the particular tables that we're interested in, and then basically executing those as SQL statements against our destination database. This is what allowed me to copy the insert and update issue statements into the new database. In practice, what we will do here likely is consume most of the queue, and then we will pause writes, which we haven't got an implementation for yet. So we'll block any updates, more updates coming through that queue for that specific group that we're copying across. And then we'll just consume the rest of the queue to make sure that we're caught up with any updates that happened in the time between the last check and pausing writes, which should be a small amount. Once we've copied those small amounts across to the destination database, we can then unpause writes after we've switched our references to point to the new shard. That code hasn't been written yet. Now, going back to the foreign keys at the top here, some interesting parts of this I learned throughout were some tables have cyclical foreign keys. So for example, the namespaces table seems to also reference the namespaces table in a foreign key with a column called custom project templates group ID. This can make it quite difficult to do an initial copy of data because you need to make sure that the referenced foreign key exists in the database before you can create the group that references that foreign key, so that we don't have any violations of that constraint. I had a look in the application documentation for this feature, and I believe it implies that this feature will be logically consistent with namespace sharding or top-level namespace sharding, as it suggests that you are required to have these template groups defined in the same top-level namespace as the group that you're adding them to. But the database foreign key constraints cannot guarantee this, and it's entirely possible we have a bug in our application at some point in time, and the data in our database is inconsistent, and one of these foreign key references a namespace that's outside of your top-level group, which would thereby make it impossible to copy that namespace across to a different shard without violating this foreign key constraint. So that's something to be aware of when we do these kinds of migrations. Many of the foreign key constraints, as I mentioned before, are just related to users, which is just a global problem we're going to have to solve because users aren't part of namespaces necessarily. And in general, just importing things that have foreign keys, even if they are going to be correct at the end of the import phase, is going to require a careful implementation to make sure that the foreign keys are not inconsistent during the copy. So any references to foreign keys need to be exactly available at the time of insert, and maybe that requires inserting two things at once, or maybe there is particular challenges with how to do that. Maybe things have to be inserted and foreign keys added later. Other features of GitLab may just have to have foreign keys removed if they can't be consistent with namespace sharding. If we were to drop all the foreign keys to do the initial import and then not use foreign keys entirely, this may be an easy implementation for copying data across, but it wouldn't reveal any data inconsistencies where we may have foreign keys that are actually outside of our shard. So it's probably also not great to do it that way because we will just have things that are referenced that we can't find later when we do a join query and so on. This is just a demonstration of what it looks like with 3 tables, and there are already some issues with the foreign keys just for these 3 tables, but when we actually come to implementing sharding for top-level namespaces for all of the tables that relate to a namespace, it's more like about 200 tables. We haven't got the exact numbers, but if we were to do all 200 tables, we expect that we'd find many more issues. One specific issue that we did find also here for the issues table is that if you have an issue, you can move it to another issue in GitLab, and we don't actually require that other issue you move to is in the same top-level group. So it's entirely possible that we have foreign key references of moved issues or duplicated issues that in fact are not in the same shard. And this feature will, at the very least, need to have the foreign key constraint removed, but it'll also be pretty tricky to implement the efficient queries for loading those moved to or duplicated IDs because they are going to belong in a different database, and we won't actually know ahead of time until we look up the issue across all shards where that issue belongs. That is all for the demo, and thank you for watching.